good answer to that. We already have 3. Huh? That would be this. That would be the amplitude. I want to know the value, like on that axis. What if that's distance? Not an angle, not a time interval, but distance. What's that? What is this distance? A wavelength. So how much is this then? 1/4 of the wavelength. Yes. What would this number here be? If it's an angle in radians, it would be pi. If it's an angle in degrees, it would be. If it's a period, if the horizontal axis is time, this would be. And if the horizontal is a distance, this would be. Right? And then this one would be, corresponding to the, what's this, 3/2 pi? Excuse me, 270 degrees. In time, that would be what?
3/4 t.
3/4 of a period. And in distance, 3/4 of a wavelength. And this point here would be 2 pi radians, 360 degrees, a full period, and a full wavelength. What would this point be in terms of radians? Let's say that's the maximum there. Right? So 5 pi over 2, correct? In other words, 2.5 pi. This is 0.5 pi, pi, 1.5, 2 pi, 2.5 pi, 3 pi. Yes. In terms of distance, what's this distance over here? What's
1.5 wavelengths.
What's that?
1.5 wavelengths.
Right, 1.5 wavelengths or 3/2 wavelengths, right? I guess, and in degrees it would be what? 360 plus 180? 540? So, whenever you talk about, blah, 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 sine of blah, 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 or blah, 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 cosine of blah, 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 the argument, whatever goes in here, whatever goes in there, it's called the phase. So, if I draw, and I wish I had my transparencies, but I don't. If I drew, and I'm gonna mess that up. If I drew another wave, like this, so that there are two waves, a blue wave and a black wave. And I ask, what's the phase difference? So look at one point, like let's say this point over here where they sort of, although this continues backwards, but let's say this is where they begin. By how much do they differ in, the phase is an angle, right? By how much do they differ? Zero. So you say that the blue wave and the black wave have a phase difference of 0. Yes. And when the phase difference between them is 0, you say that they are in phase. Now, what if I drew another wave? Forget about the blue one. Let's focus on the black one. And I drew another wave like this. And I ask you, what's the phase difference between these two waves?
90 degrees.
You could say they are 90 degrees out of phase, or they are pi/2 radians out of phase. Or the phase difference between them is 90 degrees. The phase difference between them is pi/2 radians. But if I think of this as a distance, right, and I ask you, what is the path length difference? It's the difference in the distances traveled by the waves. If I think of this wave as starting over here and this wave as starting over there, what is the extra distance that one wave has traveled relative to the other wave? The path length difference. A quarter of a wavelength. So if you consider the purple wave and the black one, right, you can say the phase difference, I just use it, that refers to an angle, is pi/2 radians. That's a good answer. Or you can say 90 degrees. Now, if I ask you what is the path length, it's like the length of the path that was taken by the wave. But I want the difference between that one and the black one. Since I want the difference, then this extra distance is, wavelength is a distance, right? It's a quarter of a wavelength. What if I draw another wave, and the other, I'm going to use a different color. I'm still using the black one as reference, and I draw another wave like this. Right. Now I'm going to write it over here, and I ask you, what is the phase difference between the green one, the green wave, and the black one? 180 degrees, or pi radians. And if I'm interested in the difference in the distances traveled by the waves, what is the path length difference? Half a wavelength, λ/2. And if I talk about a time delay between the black and the green one, a time delay, like, how much they differ in time, half a period. I'm going to draw another one. Let's see, do I have another color here? Ooh. Is this orange? Mm-hmm. Okay. What if I have another one interfering with the black one, and I'm going to draw it like this? I'm sorry, this is getting okay. So now, what if I ask you, referring to the orange one, for the phase difference with the black one? So what's the phase difference between this one and this one? 270 degrees, 3/2 pi. And what is the path length difference between them?
3/4 of the way.
is 3/4 of a wavelength. Yes. So, oftentimes, like I'll be talking and I'll be saying the path length difference and the phase difference and I'll say some angles, and what does that mean, right? So it means this. So 90 degrees, 180 degrees, 270 degrees, 360 degrees. In radians, I'm a little bit slower with the radians, right? pi/2 pi. That one I usually have to stop 3/2 pi and then 2 pi. Distances, I'm pretty quick, 1/4 of a wavelength, 1/2 a wavelength, 3/4, 1 full wavelength. The period is just like the wavelength, so 1/4 of a period, 1/2 a period, 3/4 of the period, 1 full period. So what we're interested in this chapter and in the next one, chapter 36, is in the problem where you have two waves that have the same wavelength. That makes it very, very, with all the difficulty that's in the topic, that both of them have the same wavelength simplifies the problem immensely, and that's what we're going to be focusing on. And you have two waves of the same wavelength overlapping in space at some point. In other words, interfering with one another. What will be the resultant wave that you're going to get? When these two waves interfere, and it's by the superposition principle, the resultant wave is the sum of the two individual waves. But what do you think we're going to get if I interfere, for example, the black wave with the green one?
Nothing. They cancel out totally.
They'll cancel out, exactly, because it's like, imagine a rope where the green wave is pulling the rope up, but the black one is pulling it down. And we're also going to consider same amplitudes. Same amplitude, same wavelengths, so that since these amplitudes are the same, like plus A and minus A is just going to give you 0. So we're going to talk about constructive interference. Constructive interference is when one is on top of the other one so that they reinforce one another, giving you a maximum. So constructive interference refers to a maximum condition, reinforcement. And so if I ask you for two waves that are traveling in space and they travel and interfere at some point, what should be the condition for constructive interference? So if I say, okay, if I want to write a condition for constructive interference, and that means, maximum bright. If these are light beams, you're going to get maximum intensity, so it'll be bright. In phase is what's meant, in phase. Those are words that mean constructive interference. Bright, maximum, in phase, constructive, reinforcement. Those are words that mean the same thing. Maximum interference. Now, what are the conditions for constructive interference? So, if I talk about, the symbol that's used to denote phase difference is like a change, a difference is a difference in angle, and the angle that's used is, so this means like a change or the difference in an angle. Because remember that a phase is an angle, right? I can think of, an angle, overall this over here is phi, overall this is phi, so the phase is phi, and if I want the difference, then I want the difference in angles. So the notation for phase difference is this. Now, can you tell me, I'm going to erase these values over here. Can you tell me what the phase difference has to be between the black wave and any other wave so that you get constructive interference? So where would I draw the other wave, to start with? Starting over here, right? So it would be 0. But is there another case where I can draw another wave starting somewhere else, so that there's a phase difference, that will still give me a maximum when they interfere. Yeah, what if I started over here? That'll be 2 pi. And then the next one is gonna be out here, 4 pi, right? And then you can see the pattern. It'll be 0, or if the phase difference is 2 pi, or 4 pi. And now you can see the pattern, right? 6 pi, 8 pi, 10 pi, 12 pi, so on, right? So, can I erase this now? I need some room over here. So in general, I can write this as 2m pi, where m would have to take on which values so that I get all of these possibilities over here. What would have to be the value of m so that I get 0?
And 0.
0. What would have to be the value of m so that I get 2 pi?
1.
And what would have to be the value of m so I get 4 pi?
2.
And then you can see the pattern, 3, 4, 5. So it'll be 0 or a positive integer. So this is just a general condition for writing down constructive interference. Now, what if I ask you what would have to be the path length difference for constructive interference? And the symbol that's normally used for this is alpha. I think that's, let me be consistent with my notes. I think that's what it is. Actually, delta, not alpha. I didn't see it over there, but I think, let me go back and check, but usually I call it delta, or it's called delta. And some authors of textbooks use different notations, so I just want to remind myself what the notation is by the author of this textbook.
Isn't delta a triangle?
Oh, they call it R2 minus R1.
That's like the letter for it, other than that.
Oh, okay.
They call it R2 minus R1. Same thing, like the distance traveled by wave number 2 minus the distance traveled by number 1. So they call it R2, the distance traveled by wave number 2 minus the distance traveled by wave number 1. So it's the path length difference, which I'm gonna call it delta also. Now, what would have to be the difference in the distances traveled by the waves in order for the waves to interfere constructively? What are the
0. Or wait.
0? What else?
One wavelength?
One wavelength, right? Notice, one wavelength is the same as 2 pi, right? 2 pi will be one wavelength. 0 goes with 0. And 4 pi is going to go with
2 wavelengths?
2 wavelengths. And then
3 wavelengths?
3 wavelengths. So in general, this will be m lambda, right? Where m is the same, with the same definition. Where m is this, right? So for constructive interference, we have these conditions. Does that make sense? I mean, I want you to understand, because we're going to be using this, and then you say, what the hell does that mean? You know, what's delta phi? You know, what's phase difference? What does it mean, right? I mean, you can memorize it. I'll give you some formula, but then and use it. But then I want you to have an understanding of what this means, right? Let me give you an example. I will erase this. And this. So, what if I tell you that there's a source of light over here? And it doesn't have to be light, this could be sound waves also. Let's say S1, source number 1. And from this source you have point over there, and then here's another source. Light source. Number 2. And same wavelength, and also they are in, when they emit in phase. So they both emit at the same instant. So let's say that the wavelength is 2 meters. Let me write meters because I don't want you to think 2m and think of this m as that m over there. That's just an index over there. And then they're going to travel, and then they're going to meet over here. And the question is, what if this distance over here is 12 meters? And this distance over here is 8 meters. When they interfere over here, will they interfere to give me a bright spot or a dark spot? Which is it? Bright or dark? Bright or dark?
Right.
How do you know it's bright?
The phase difference is 2m wide, not 2 m lambda. So I mean the outline difference is the same.
So, okay, so let's work it out. What is the path length of the wave coming from source number 1? What is the path length? 12 meters. And how many wavelengths is that?
6.
Okay, so I'm gonna, let me sketch it, let me draw it, right? So I'm gonna go, so since the wavelength is 2 meters, right? That means that this is, one wavelength is 2 meters. So in a distance of 12 meters, I can fit 6 wavelengths, right? So that would be 1, 2, 3, 4, 5, 6. And when it gets there, it starts a new wave, right? Now what about the other one from source number 2? The distance, this 12 is like R2. This 8 is R1. It's the distance traveled by that wave, right? And so for this one, how many wavelengths will we fit in there if the wavelength is 2 and the distance is 8 meters?
4.
4. So then I'm gonna go, and I'm gonna start this in phase with that one. I shouldn't say, let me start them in phase. They are said to be coherent, like they start the same condition. So this is 1, 2, 3, 4. And when it gets there, it wants to start a new wave also. So notice that for both of them, the blue is going to add to the green. So it'll be bright. Now, what is the path length difference? R2 minus R1 is 12 meters minus 8 meters, right? Which is 4 meters. But I can convert this to wavelengths. Notice that one wavelength is 2 meters, right? So this cancels that. And I get that the path length difference, R2 minus R1, which I like to call delta like that, is 2 lambda. And because it satisfies this, that happens to be this one, it's constructing interference, therefore it's bright. So this satisfies path length difference is m lambda with m equals 2, which is one of the allowed values. M can only be 0, 1, 2, 3, 47, 153, some positive integer or 0, then it's bright. Yes? Or no? We gotta get past this so that the rest makes sense.
So the angle that they come in and meet each other at doesn't matter.
Usually we're going to say, they're coming like together, like, with no angle, yeah.
Okay.
So what we're going to consider are, like in the lab, we're going to consider 2 slits that are probably 100 micrometers apart. And then we're going to look at a screen that's far away. So, if I'm over here and I look at 2 dots that are really, really close to each, like they're coming together. And so The only way to make the two sources coherent so that they emit in unison is if you really have just one source and you make it go through the same wave emitted by the same source, goes through two slits. And then we think of the two slits as two sources, but it's the same wave that was originated by whatever was emitting it, and we're just thinking of that as two sources, but you still have just one emitter behind that. So, if I were to write down conditions for destructive interference, what would I write down? What would have to be the phase difference between the waves when they interfere destructively, so that one wave cancels the other one? So if these are light waves, you get darkness. If these are sound waves, you get silence. Minimum. Cancellation. Those are words that are used to describe destructive interference. Can I erase this example now? So I can use this side of the board to write a condition that has to be satisfied for destructive interference to occur. So for destructive interference, and that means what? Cancellation. Does cancellation have one or two L's? One, right? Two, right?
I guess too.
Yeah, it looks weird with only one. Darkness. I should say silence if the waves are sound waves. Minimum. And people just say out of phase, but it's really 180 degrees out of phase. You know, there are other descriptions. And what would have to be, number one, the phase difference between the waves that interfere with the same amplitude and the same wavelength, but they interfere in space. So what would have to be the phase difference?
Kind of give us.
I wrote difference, but I didn't write down the word phase. And phase difference refers to an angle, either in radians or degrees. So where would I, if I'm interfering the black wave with another wave, right? What would have to be, where would the other wave have to start so that, or by how much of a phase should it differ from the one in black so that you get cancellation?
180 degrees.
Pi, or 180 degrees, right?
You kind of gave us the answer. Right?
Huh?
You kind of gave us the answer already in the, right there,
Yes.
180 degrees
Yeah,
out
exactly.
of phase.
That's why it's, usually you just pick that first value. Because there are other phase differences that lead. But usually people just give you an angle between 0 and 360 degrees, so 180 degrees is the first time. So pi, what would have to be the next one? 3 pi, correct. And then you can see the pattern, 1, 3, 5, 7, 9, 11, 13. So 5 pi, 7 pi. Now, can we write this in a mathematical form that's closed? So we can say, how about we say 2m plus 1 pi? Where m would have to be, now let's think about it. Given my way of writing it like this, what would have to be the value of m so that I get the first value over here? 0. What would have to be the value of m over here so I get this value? 1. What would have to be the value of m so I get this value? And then So notice that if I write it like that, I can use the same allowed values of M as for constructive interference. What I tend to do, because sometimes you solve problems where you have combinations of constructive and destructive and blah, blah, blah. What I tend to do in this is just me, I don't think the authors of the book use it, is that whenever I'm talking about destructive interference, I like to put a prime. That reminds me, we're talking about that, that's just me. From my understanding, I tend to put a prime. You don't have to, but I tend to put a prime so that I differentiate, so that I know that I'm talking about destructive interference, not constructive interference. Now, what about the path length difference? That would be like a delta, which is R2 minus R1. That's the path length difference. It's three words that mean something simple. Path, that's the path taken by the wave. The length of it is the length of that path, but then it's the difference between that path length and the other path length for the other wave. So path length difference. You say it together and it sounds like, oh my goodness, that's difficult. But once you understand what it means, then it's no big deal. Path length difference. What would it have to be? So, what's the path length difference? Lambda
Wavelength.
over 2, half a wavelength. What's the next one? Three halves or 1.5 wavelengths, right? So 3/2. And now you can see the pattern. This is 1 lambda over 2, this is 3 lambda over 2, then 5 lambda over 2, then 7 lambda over 2. So once you write a couple of these, then I can write the other ones. So how do we write this? You could write it like this. Because what would have to be the value of M prime so that you get this? 0, which is this. What would have to be the value of M prime so you get the second allowed value? 1, because 1 plus a half is 3/2. And that's 1. What would have to be the value of M so that you get this value? It would have to be 2, because 2 plus a half is 5/2, which is this. So notice, if you write it like this, then with this, you can still get, destructive interference. Yes? Or yes?
Yes.
So again, you see this on the board and you see, pi's and M primes and M's and phi's and delta, and it throws you off right away. Right? So spend some time thinking about what they mean. Like, what do you mean phase difference? Right? So just think of one wave advanced relative to the other one. So by what phase, by what angle should they differ? And that is, isn't just one angle, there are many angles for which they could differ, so that when they interfere later on somewhere else, they'll interfere constructively, right? So there are various angles, right? And I wrote it over here in terms of radiance, and I wrote it over here in terms of, it's like the same condition, but in terms of a distance that the waves travel, the difference in the distances traveled by the waves. Okay, so let's consider the light going through 2 slits. So I need to erase the board.